Hello, class. All right. Last time we talked a bit about binary search trees. In fact, I still have it up. We talked about how they were built, or we talked about trees in general, and more specifically binary search trees, which is what I've got built here, and a couple of different ways to traverse it and look through it. So what we're going to do is we're going to talk about how you build one of these today. Now, first, obviously, you make a project called binary search tree. You can date it however you want to do it. And in that project, you're going to have to basically right-click New Java class and create a node file, which is what we have here. Now you're going to name it node. And if you capitalize it, it needs to be capitalized in other places too. Now this is very, very simple. I just have a data, a node left, node right. So if you remember, we talked about linked lists before. Basically, these two are pointers that point to one direction on this tree. In our binary search tree, we have a left that points to the next node on the left, a right that points to the next node on the right. In a linked list, you had a next, which pointed to the next thing in the chain. A tree pretty much is the same thing, it's the same idea. We use that pointer to point to the next node. Left, right, left, right. And if there's nothing there, then it would point to null, or empty space, pretty much. And that's how we would know how to put something there if we needed to. Now, I made all these public by not referencing that they're private. If I did say they were private, I would have to make some get and set methods for these, but only if I make them private. I got a little lazy. Technically, it's probably better if data left and right were private. You would need get methods. And, int data would be public int get data, and you would return data. The node left would be public node get left, and you'd return left. Same thing with this get right. Feel free to add those if you want, but we're going to keep it as basic as possible here. We have one constructor that just builds our node. I give it a number in this case. It plugs that number into the slot, and the left and right are null. Now, the node itself doesn't really do anything. It just makes a little slot to hold my stuff. This node will be inserted into a binary search tree. That's where the actual use for this data structure comes in. Now, let's take a look at the binary search tree. So, binary search tree. Also fairly simple. I've got a lot of stuff here that's just crossed out, but you'll see. You'll right-click, New, binary search tree, Java class, if you're using NetBeans like I am, or Eclipse. We're going to have one public node root. This is basically like we consider it like the linked list. It's like the head. This is the top of our tree. So effectively, it's going to be this top item here. This is the root node. And that allows me to get to any other node in this tree, because every node has to be connected to it in some form or fashion, either through left or right. Now, when we create a binary search tree, we're just going to make a binary search tree with an empty node at the top. This .root is null. And then, when we insert, if it's empty, well, we'll put our node in that slot. If it's less than the number, then we go to the left. If it's greater than, then we go to the right. Those are the typical rule. Now, I've adjusted mine a little bit more so that, we could say if there's a duplicate, spam out, you can't do that. The way I dealt with it was basically it's going to go to the right. So if I get a 10 again, well, I would go to the right. If it's less than, or if it's less than or equal to, rather, it's just going to plugged in here to the right side of this. And then I think I said to the left. So if it's less than or equal to, it'll just go left. If it's greater than, it'll go right. Now, our regular insert. I actually have two kinds here. One is a recursive insert, and the other is a regular insert that just uses loops and whatnot. So let's take a look at the regular insert first. First things first, we create a node with the data we want to insert. So I just make a little circle, boop, plug in my number, set to the side. Then I have to go into my tree and figure out where this needs to go. Now the way a tree works, I'm not going to plug it here and then move everything around. I'm going to find the first available space according to my rules. And the rules are less than we go left, greater than we go right. So if I want to insert a 6, for example, that's less than 8. But it's greater than 4, it's greater than 5. The 6 would actually go right here to the right of 5, based on my rules here. Now, very first thing, if the root is null, means my tree is empty. I can't put anything in there. So I just set the new node that I made to the root. I plug it in the top. Boom, there you go. Now, else. That goes down to almost the end of this, the bottom. You'll see end of insert. There it is. Tree has stuff in it we have to traverse. Now I'm going to need a temporary pointer to point to the root, basically. And that allows me to move that down without moving the root. If I say root equals root.left, for example, well, in my tree, root equals root.left. Now that's the root. I just cut off the entire right of the tree. It doesn't exist anymore. So I have to have another pointer, like we did in linked lists. I have a little temporary pointer that pointer moves down, but the root still points to the top. Now, else. I make my temporary pointer. I have a parent pointer to keep track of the one before. And then I say while true. Now, while true is basically just an infinite loop. So it's kind of I don't know how far I need to go down. I don't know where it is. So I just use a simple while true, and I'll return out of this method when I'm done. Now, parent equals the current that we're at. And then I'll move the current thing down one. So if the data is less than current, then I'm going to go left. So current equals current.left. So the way that looks visually, parent would point up here. Current would move to the left, and I would be pointing here. So I still have access to that node above me. And then I'm here. So current equals current.left, that moves me left. If that current is null, that means basically this. I've gone down my tree, and my current is here. It's null. That means I'm where I'm supposed to be. I can't go left or right anymore. This is where my number is going to end up going. So if I were inserting, I guess in this case it would be hard to insert something here that would be between that, let's say 4.5, for example, if I was doing doubles. It would be greater than this, but less than that. I'd be here looking, and as soon as I found a blank spot, that's where it would go. So basically this says if current is null, then I'm where I need to be. Parent.left equals the new node. So if you know parent is pointed at the previous item. So if I wanted to put it here, my current would be here, my parent would be here. Parent.left is that new node. So I'm just pointing that pointer to that node. Now, and then I print off, it's pointing, and I return. Notice I've returned nothing. Basically, what I'm doing here is just returning out of the method, out of the loop, and that ends this loop forcibly. Now, else. Well, data is not smaller, so I'm not going left. There's only one other direction I can go, and that's right. So I shift right. And I do the exact same thing. If current equals null, then set up the node, put it in there. Now, this loop goes here. And notice this says if data is less than, go left. Else, I go right. And inside of each of these is if it's null. The only time I'm going to insert something is if I find the null area. And then this loop's going to come again. So let's outline how this works. Let's say I want to insert a 12. I start here, parent is here, current is here. 12 is greater than this, I shift the current left. Parent is going to be here. Now, is current null? No, it is not. So according to my code, since that is not true right here, none of that code runs. I just go to the end of the while and come back up. And then I do this again. If current.left, is less than current data, go left. If it's greater than, go right, or greater than or equal to in this case. So 12, well, I'm going to go right, it's greater than that. Parent goes down to the right. Current goes down. Is the current one blank? No, it's 20. So I can't insert. I don't insert. All right, well, 12 is less than this. Current's going to point here to this null. Parent's going to point to the 20. Now I've gone left, and I'm at null. So code-wise, if data.left is less than, we just did that. We set the current. If current is null, it is. Parent's left points to my new node. So the parent, which is 20, I point that's left to that new node that I just created. Just like that. And if it was going right, it would do the same thing. So that's effectively how insert works. Fairly, hopefully, simple. You kind of hopefully follow that for the most part. You just kind of have to know that the parent is always going to point one above, and the current moves left or right depending on if it's less than or greater than. And then I move them both down to whichever direction they need to be. I check, and basically I'm just looking for an empty place to put my number. That's effectively all I'm doing. Now, if it's the same, it's going to go right, if you notice. I say if it's less than, go left, but if it is, I didn't say less than or equal to, I said just straight up less than, which means that the larger number will go right. So if I insert a 20, that would go here to the right. And I can insert duplicates. I didn't write anything in there that said you couldn't. If, it's the same as something that's already in there, that is not what I said. So I can insert duplicates in this particular thing. So let's take a look at our tree. That is regular insert right here from beginning to end. I'll spread that up a little bit more so we can kind of see the whole thing. There you go. Brace by brace, and else, and while, if here, like so. Now, I do have a recursive insert, and honestly I don't like it as much because recursion usually works faster. There's usually less writing involved, but if you notice, my insert is 33 lines, my recursive insert is 31 lines. Plus, there's this get successor, which is actually used by the recursive insert, basically. Actually, no, the get successor is used by the delete. I take that back. This is like a few lines shorter than our regular insert. But it doesn't use loops, that's the thing. It uses recursion instead. And in case you don't know, recursion is when basically a method calls itself again. So in this case, instead of using a loop to go down this, I would say, I want to insert. Okay, I can't insert. I move myself left, I want to insert. I can't insert. I move myself right, I want to insert. Nope. I want to insert. I insert. That's effectively what happens. And then I back out of all those methods with a successful insert. So this is, I have to give it the data I want. I have a current pointer and a previous pointer, basically parent. And if both of those are null, then I'm in the place where I need to be. If one is null, but the parent isn't, then I have to decide which direction this is going to go. Now, the else, that means the current's not null and the parent's not null. That means I need to move left or move right, effectively. So I come down here and check which direction do I need to go. And I call insert again, which moves me left and tries to insert again. Moves me right, tries to insert again. And actually, this is probably a couple of lines shorter, but not by much. That's your recursive insert if you want to go ahead and write that. They do essentially the same thing. They just do it a little differently, so it's interesting to see the different setup. Instead of using a while loop, I just recursively call it instead. And typically that's a lot more effective, a lot faster, a lot more efficient than just running loops. If we timed it, I don't know if we'd notice much of a difference or not, but this would be recursive insert. From beginning to end. Like so. But again, it does the same thing that insert does. Now get successor is used for delete. So I'll go through that real quick. Insert's a fairly easy activity. I just find a place where my thing needs to go and I insert it. Delete, on the other hand, it's a whole nother problem, a much more difficult problem. If I want to insert, I just go down this list until I find an empty spot to put it. Now if I want to delete, if it's one, piece of cake. I just, this dot next, there, this dot left does equals null, this one's gone. But what if it is 4 I want to delete? Well, I've got all these nodes below it. If I just remove it, I cut off the entire tree. I have to move things up, basically, if I want this thing to work properly. If I delete 10, then what should go up? Well, 9 or 20. Depending on how you write it, technically either would probably still work. 20 is still bigger than 9. 9 is still less than 20. We'll see how it looks once we get to it. Now, the get successor is basically trying to figure out what node needs to move up when you delete something. So let's just take a look at that. It's fairly short, as you can see. And this right here is basically just going to go down the list until we figure out which node needs to be the one to go there. So node successor equals null. I know which node I want to delete. So this is the pointer to that node I want to remove. Node successor parent equals null. Node current equals delete node dot right. So I'm going to check the right first. So current's going to point to the right item. So if I were to try to delete 10, the current's going to point to 20 right now. And what it's going to say is, as long as the current, while the current isn't null, successor parent equals successor, successor equals current, current equals current dot left. So what is this going to do for me? We're going to move down until we find an appropriate thing to move up. So basically, we're juggling these things around. So effectively, what I'm doing is moving the tree up. Let's take a look one more time real quick. Successor parent equals successor. Now, successor is null at this point here. Successor parent is null. Current equals whatever the node's right is. Whatever's right of that node I'm deleting. While current's not null, successor parent equals successor. back on. My headset cuts off after like 20 minutes or something. So, of no sound being sent to it. Anyway, as I was saying, node successor parent equals null, node current equals delete node right. So I'm going to move right and check. While that right is empty, we're going to start juggling some stuff, basically. Notice successor parent equals successor, which at the beginning of this is null. But successor equals current. Current equals current.left. So I'm basically moving all these pointers down until I get to current being a null. That means basically I've gotten to the end of this here, right here. Current's there, successor parent is up, and so on. So we come down here and we check if successor does not equal deleted node dot right, then successor dot left equals successor dot right. There's a lot of, like I said, there's a lot of confusing code here. I know. I'll try to explain it as best as I can. Successor right equals deleted node right. So basically, we're moving things up is what's happening here. I move myself down until I get to a place where I can bump something up, which is kind of what we're doing here. If successor does not equal deleted node dot right, then what do? Successor parent dot left equals successor dot right. Successor right equals deleted node right. So I'm basically just, I want to delete 10. Okay, it's gone. Poof. And it would totally let me do it if I use select instead of just highlight. All right, 10, you're gone. So now I got to decide which one of these guys is the successor. So let's look at the code again. Successor parent equals successor, which is null. Successor equals current, which is not null. Current's the deleted node right. So current will point to 20. Successor parent will point to null at the moment. Successor right equals deleted node right. Let's see. Oh, wait, we're up here. Current equals current dot left. Now, there is no current dot left in this case. It's null. So we'll loop back up. Current's null, so this whole loop's going to stop. So successor looks to me to be 10, or in this case 20. We come down here. If successor does not equal deleted node dot right, well, in our case it does. So we would skip all that and we would return 20. 20 is the successor that we would bump up. So basically I would just take that and it would go up. Like that. I'd plug it in there. Now, of course, if there's the difficulty here is if there's more stuff under it. That stuff has to move up. That stuff has to move up. So all this getting successor is just getting the successor for that one node. Now, keep in mind, this isn't delete. This is just the part that gets the successor for one node, basically. So basically, this would move 20 up. Now, if by chance there's more, then I would be calling get successor again for that node because I'm deleting it. Basically, I'd be calling delete, delete, delete. Let's say I deleted 8. I would have to move 10 up. All right, that would move. But then I would have to delete this 10. So I would delete that 10 there. But then I have to move the 20 up. And if I deleted the 20, well, that would just be deleted unless there was something else, and that would have to move up. So there's this whole chain reaction that happens if you delete something in the middle of the tree. So we come back, take a look, and then we have delete, find, in order, pre-order, post-order. And we'll do that in the next video here. So we'll walk through that here in just a few minutes.